Let's try and see how light behaves when it passes through a diverging lens. So we place an object somewhere quite far away from the diverging lens or concave lens as we usually call it. So now we'll see how light travels. So let's send a few light rays and see how it behaves when it encounters the lens. The first ray will be a ray that is parallel to the optic axis. So once it strikes on the lens, you encounter a change in the medium, probably from air to glass, and because of the change of medium, you experience refraction. To determine the direction of the refracted ray, we need to first determine the normal line. So this curve here, you can extend this curve to see that this curve is formed by a circle, which is on the left hand side. So we'll be drawing the normal line based on the center of curvature over here. So extending a line towards this point where the light incident on the lens. So this is our normal line, and from our normal line we can try to determine where will be the angle of refraction. We know that it will be entering a medium which is denser, a medium with a higher index of refraction. Therefore, it will be refracted towards the normal. So you can see that the angle here is larger when compared to the refracted angle over here. Okay, so you continue to travel and hit the second change of medium over here. So you go from a denser medium, a higher refractive index medium, to a less dense medium or a lower refractive index medium. So now once you reach this point, this surface here belongs to this center of curvature. So draw a line out to represent the normal line. Then we will try to determine the direction of refraction. We see that the direction of refraction, if you compare, the angle here is smaller, whereas the angle of refraction here is larger. So this is aligned with what we say just now. When we enter from a denser to a less dense medium, we experience a refraction that is away from a normal. So you can see that the angle of refraction over here will be larger compared to the angle of incidence. So this is what we determine for a light ray that passes through the lens while it is being parallel to the optic axis. So we leave the refracted ray over here because I want to draw the other rays and I don't want things to be too messy in the whole diagram. So I just keep the refracted ray here just for purpose later. Okay. So the second ray will be a ray that is aiming towards the focal point that is on the other side of the lens. Okay, we know that light it will pass through, but let's say if we aim the light rays in the direction where it will be passing through the focal point on the far side of the lens, then you see that refraction will occur as well. So this surface here corresponds to this center of curvature. Draw a normal line, then you'll find that this ray here will be bent towards the normal, small angle, larger angle. Second surface, this surface corresponds to this center of curvature. Again, another normal line. It's getting a bit too complicated for us to see things right now, but I believe you know that you get refracted away from a normal because it's entering a less dense medium. So once it's bent, you'll find that this ray here will be parallel to the optic axis. Okay, so if you send a parallel ray, you will get diverged out with respect to the focal point on this side of the lens. Whereas if you send a ray that is aiming towards the focal point, you get bent to be parallel. You can think of these two rays as an opposite actually. Okay, just like you send a ray this direction, you send it parallel, then you get diverged out. Whereas if you send a ray which is aiming towards the focal point, you get back the parallel ray over here. Okay, so that's two of the rays. Let's remove all the unnecessary things. We only look at the refracted ray. Right now it's considered diverging. So I believe you know why I keep these refracted rays. So the third one will be the ray that passes through the center of the lens. Well, again, if you pass through the center of the lens, there's something happening inside here, but since it's too minute, it's too subtle, so I choose not to elaborate on it. You can just think of it as traveling as a straight line with a little bit of distortion, which is negligible if it's a thin lens. Okay, so if we keep these three refracted rays, we see that all three refracted rays are diverging away. So technically there will be no real image formed over here, because real image requires intersection of the actual refracted ray. But if we extend all these refracted ray backwards, we'll find that all these refracted rays actually intersect at one point over here. So you see that all these are extension, therefore the image that you form here will be a virtual image. So you form a virtual image if you place your object over here. Okay, the purpose of this explanation here is just to show you how the light travels, how the light bends when it encounters a change of medium. So now I'm going to introduce to you the proper way of drawing the ray diagram. So again, for ray diagram, we do need to show that the refraction happens twice. Theoretically, it did happen twice, but you just need to show the bend at the mid-plane of this concave mirror over here. Again, mid-plane is a plane that is in the middle of the lens. So you place the object again at a similar position, then you send in a set of rays. So all three rays over here have direction of refraction that is easy to be determined. That's why we choose these three rays here. Okay, the first ray parallel, then it will be diverging away with respect to the focal point on this side of the lens. It will send in a ray which is aiming towards the focal point on the far side of the lens. Then see that the refracted ray will be parallel to the optic axis. Lastly, the third ray will be incidenting towards the center of the lens. And know that since it's a thin lens, you just travel in a straight line. The thin lens causes less distortion, which is not obvious in this diagram over here. Again, you see that there's no intersection now, but if we happen to extend the lines over here, we see that all three dotted lines here, all three extensions here actually intersect at this point. Therefore, our image will be formed at this point. Okay, when you draw your ray diagram, right, you have to include the incident ray, the refracted ray, and the extension of the ray backwards. Okay, but there's a few dotted lines which are not extension of the refracted ray. Like this one over here, this is trying to show that it is incidenting in the direction that passed through the focal point on the far side of the lens. Okay, it's just to show the direction is coinciding with the focal point over here. This dotted line here is also to show that the refracted ray here is in the direction that passed through the focal point. It is not trying to show you this is the extension, but it is in the same way the extension of the refracted ray as well. Okay, so again, they will intersect this point, so we'll call this point the image. So that's all for diverging lens. I won't show you another version of me placing the object at any other position. Why do I not do so? Because diverging lens has the same characteristics as a convex mirror actually. For convex mirror, all the object form will be virtual, upright, diminished, right? So as you can see here, the image formed by a diverging lens or concave lens here will also be virtual, dotted lines, upright, above the optic axis, same as object, diminished, smaller size than the object. So you can see the characteristics of the image formed for diverging lenses or concave lens is the same as the image formed through a convex mirror. Okay, that's why we always say concave lens is similar to convex mirror. So that's all for diverging lens.